Okay, excellent. Good afternoon, everyone. I hope you can hear me. Today we are honored to host Professor Abhay Pasupathy from Columbia University for our Q-Farm seminar. And Professor Pasupathy received his graduated from Indian Institute of Technology in Kanpur and did his PhD from Cornell University in Professor Dan Routh's group, studying electron transport and molecular transistors. He was then a postdoctoral researcher at Princeton in Professor Ali Yazdani's group. And since then, he's been a professor at Columbia working in low temperature physics, scan probe microscopy, electron transport specifically. He's also a group leader in the condensed matter physics and material science division at Brookhaven National Lab. And yeah, I think without further ado, Professor Pasupathy.
Okay, thank you. All right, so first, thanks for inviting me, and those of you there, thanks for taking the time. I will describe, I think, only the work in these two papers which are published. And if I have time, I'd like to say a few words on this, but I'm not sure I'll have time to discuss this at all. Okay, so this is going to be a talk about this business that perhaps many of you are involved in, making Moiré patterns and studying their properties. Let me start by first telling you who did the work. So these are, Augusto is one of the main people who did the work in my lab. And he was assisted by a postdoc, Lei Wang, who's now in Nanjing, and a graduate student from Corey Dean's group, Enmin, who's now at NIST. And the samples were grown by Daniel Rhodes, who's now a professor in Wisconsin. And all of this work, our gang here at Columbia, Jim Hone, Corey Dean, they make things happen. We've got some theory support from Angel Rubio's group and also Andy Millis at Columbia. And I don't think I'll have time to get into the twisted trilayer graphene, but let me just mention my grad student, Simon Turkel, who was the leader of that work. And of course, the boron nitride folks. Okay, so let me jump straight into it. And with Zoom, I cannot often see if there's a question. So if you have a question, please just shout or something. Okay, so what's the deal with making Moiré heterostructures in 2D materials? The basic idea is extremely simple. You start with, let's say, a semiconductor. Let's say I'm looking at the conduction band of a semiconductor. Then initially, if I have just a semiconductor in 2 dimensions, it has a constant density of states. And if I apply a periodic potential to this semiconductor with a periodicity that's much larger than the lattice, then solid state physics tells you that you'll break up this band into a number of subbands. And the K location of where these gaps open up is related to the wavelength of your superlattice. And if you do this, then you break up this initially constant density of states into a bunch of subbands, something that we know very well. And by doing this, what you can do is you can effectively control the bandwidth of your system. And if you work within the lowest subband, then you're effectively working within a material that has a much lower bandwidth than the intrinsic bandwidth of your semiconductor. So that's the name of the game. And the way you do this in practice is to take 2 layers of a 2-dimensional material and twist them relative to each other with some twist angle. And this was sort of pioneered by a set of mini revolutions. First, of course, isolating each of these 2-dimensional layers, and then work by my colleague Corey Dean, Jim Hone, Philip Kim, to learn how to pick up one of these layers and place it on top of another layer. And then work by Emmanuel Tutuk's group to realize that you can tear a single sheet into 2 pieces. And if you do that, then even though you don't know the lattice constant of each of the 2 pieces, you know them relative to each other. And so you can realize a precise twist between 2 lattices, even though you don't know the lattice orientation of either of the pieces well. So then, as you all know, in now 3 years ago, when this was done with twisted bilayer graphene, superconductivity was seen, and that really set off a sort of mini revolution of everybody trying to make these materials and trying to see what kinds of interesting physics could emerge in these systems. And one thing that's emerged is that it's kind of commonly seen that there are insulating phases that are driven by electron correlations in these systems. And I'm not putting down references here because there's simply too many of them at this point. But in a whole range of systems, when you create this kind of Moiré pattern, so it's ranging from twisted bilayer graphene to the materials I'll talk about, the transition metal dichalcogenides, when you create a Moiré pattern, and if I look at the unit cell of the Moiré lattice, which remember is much larger than the unit cell of the real space lattice, and I start filling in electrons or holes into this Moiré lattice using an electrostatic gate, when I reach, for example, 1 electron per unit cell, Moiré unit cell, I very commonly in these materials, you would find an insulating state, where single particle physics would tell you that it should be a conductor. And so this kind of behavior, which reminds us of a Mott insulator, is very commonly seen in these materials. And the first part of my talk is going to be a discussion of one particular system of these many different systems. The particular system that I'm going to discuss is tungsten diselenide. It's one of these transition metal dichalcogenides. And that looks like graphene, except it has tungsten and selenium. So it's tungsten and selenium on the top and bottom. And if I look at it at this from the top, it looks like boron nitride or graphene. And what's really nice about these systems is that if you look at the low energy physics, they look like a direct band gap semiconductor with a fairly large band gap on the order of 2 eV. And they, like graphene, their physics has 2 values, K and minus K. And at each valley, because of strong spin orbit interactions in this material, effectively there is 1 spin projection that survives. And so the resultant physics is quite simple. At low energies, there are 2 valleys, and in each one of the valleys, there is 1 spin projection that lives. And I should say for this as well, some of the foundational work was done by Tony Hines and his student at the time, Kin Phai Mak. Now, Tony, of course, is there, and Phai is at Kona. Okay, so let's take tungsten diselenide. And I'm going to be talking about transport experiments, and all these transport experiments are done in the valence band of tungsten diselenide. So let's just zoom into the valence band. And so the band structure of the valence band of tungsten diselenide is just this. It has a band with 1 spin projection at the K point and a band with the opposite spin projection at the minus K point. And the name of the game, as I said, is to take 2 of these layers and twist them relative to each other and place them on top of each other and see if something interesting happens when you create this kind of twisted structure. And so first, let me sort of lead you through what DFT level theory would tell you for what the electronic structure of this twisted material should look like. So here's what DFT tells you the electronic structure of the twisted material should look like. And this looks formidable, but it's actually not that bad. So what you should realize is that when you have a twist between the 2 layers, then the tops of the valence bands are at different points in momentum space. And this solid blue line is the valence band of one of the 2 layers, and this dashed blue line is the valence band of the other of the 2 layers. And so in general, these 2 are degenerate if there's nothing to separate the 2 from each other. But at the point where they touch each other, then electrons can hop between the layers, and this creates a hybridization gap. And so what's left at the end of the day is a single band, which has a mixed character between the top layer and the bottom layer, but is then just 1 band. And this band can accommodate 2 spins, either a spin up or a spin down. So in terms of what emerges at the end of the day, it's a particularly simple system. It's a triangular lattice with 2 possible spins per side. Okay, and so I said all of this. So this is the picture. This is before the hybridization. This is after the hybridization. And of course, like most of the materials in this field, Alan McDonald and his group have, lots of theory on this, and many others too. Okay, so let's go ahead and make samples of this, and let's study transport in these samples. So the way we make our samples is we take one of these twisted bilayers and we place them on top of pre-patterned electrical contacts. These are platinum electrical contacts. And this was a technique that was first, at least to my knowledge, was done for the TMDs by Klaus Enslin's group. And so we follow that same technique. And then we have dielectrics that isolate this bilayer from a top gate and a bottom gate. And in this system, if you apply the same voltage to the top and bottom relative to the tungsten diselenide, then you end up adding or subtracting charge from the tungsten diselenide. So that's the doping axis. And if you apply equal and opposite voltages to the 2 gates, then you end up creating an electric field. And as I'll show you, that electric field is a very useful tuning parameter of this system. Okay, so in our first work, so this is from 2020, we studied transport in this system for a range of different twist angles. And here I'm showing you data for one particular twist angle. This is a twist angle of 4.2 degrees. And I have 2 curves here, which are taken at the lowest temperature of this measurement, which at the time was 1.5 degrees Kelvin. And what you can see is that first, the blue curve looks pretty different from the black curve. So the black curve is when there is no twist angle, so the 2 of them are in their native Bernal configuration. And this black curve, I hope, looks sufficiently different from this blue curve. So 0 here is the position of the band edge, and I'll tell you in a second how we determine that position precisely. So as you start doping with holes in this case, since you're in the valence band, then eventually at a certain point beyond the mobility edge, charge begins to flow through the semiconductor, and the material becomes a conductor. And if I don't have any twist in the sample, then the material just becomes a better and better conductor. So this is the resistance. And as I dope it more, it just keeps conducting. However, if I have this twist angle that's present, then you'll see that there's a particular density at which there's a peak in the resistance. And it turns out that this peak is actually an insulating peak. So if I measure the resistance at even lower temperature, this peak resistance will keep getting higher. And this peak corresponds to precisely 1 hole per unit cell of the Moiré lattice. So that's 1/2 filling of the Moiré lattice. And you see a little weak peak at full filling of the Moiré lattice as well. And I'm happy to tell you why that's weak, but that's kind of irrelevant here. So here is a temperature dependence. So temperature dependence, if I'm sitting exactly at this 1/2 filling point, then initially at high temperature, and high in this case is down to about 20 Kelvin, the resistance is metallic, so it keeps decreasing with temperature. And then boom, I hit this temperature somewhere here, and the resistance starts increasing. And if I go away from this half filling point, so if I go to 0.6 or I go to 0.4 and I measure the resistance, then it's metallic all the way down to the lowest temperature. So clearly this state at half filling should be called an insulator, and this state at 0.6 and 0.4 should be called a metal. You can do this, so you can figure out exactly where the full filling and the 0 filling, the edge of the valence band, are by doing magnetotransport. So if you go to high field, you can see the Landau level quantization. And by projecting where these Landau levels would lie at 0 field, you can figure out quite precisely where 0 of doping is and where the full filling of the Moiré lattice is as well. And so this is a good independent check of everything else that tells us that this feature happens at half filling of the Moiré lattice. Now, we can do this measurement for a range of twist angles. So here is data for several different twist angles. And we always see this peak if you're between about 4 degrees and about 5 degrees. Below about 4 degrees, it becomes difficult to do transport. The transport starts to become unreliable. And above 5 degrees, this peak starts to disappear. And in fact, it's difficult to actually reach this half-filling point because you're not able to dope the system enough to reach this half-filling point. But within this 4 degrees and 5 degrees, which is a relatively reasonable range of angles with which you can work, no matter what angle of sample you make, they always display this peak, and this peak is always an insulating peak at low temperature. Okay, so now we do have in this system, as I explained to you, an additional tuning knob, which is the application of electric field. And so when you apply electric field to the system and you measure what happens to the resistance of the sample as a function of both electric field and doping on the x-axis, then to cut a long story short, what we found is that the region of insulating behavior is confined to a particular range of electric field. So this is for 2 different samples. So you can see that if you're at very small electric fields, the resistance of the sample is low. If you're at very large electric fields, the resistance of the sample is low. But if you're at some intermediate range of electric fields, then the resistance of the sample is high. Okay. And how can we possibly understand that in our theory? So let's go back to the theory and let's apply an electric field in theory. So if I apply an electric field between the 2 layers, then you'll create a potential difference between the 2 layers. The integral of E dot dl is delta V. And so what that means is that an electron sitting on the top layer has a different potential energy from an electron sitting in the bottom layer, which means that the valence band of the top layer and the valence band of the bottom layer now start becoming displaced from each other. And so this is shown here in this calculation. So the top box here is for no electric field, where the 2 valence bands of the 2 levels are degenerate. And then when I start to apply an electric field, then the valence band from the 2 layers now is split, and that splitting is dictated by the amount of electric field that I apply. So that's sort of the picture of what happens with electric field. And so effectively by doing this, what you do is you tune the bandwidth of this band by applying this electric field. So that's one thing that you do. Further, you'll notice that there's a point here. So this point here is a Van Hove singularity where there's a saddle point to the band structure that corresponds to a peak in the density of states. And you can ask where that peak in the density of states is relative to 0 filling or full filling of this band. And if you ask that question, here is the answer at this level of theory. The answer is that if I start with 0 electric field, this peak in the density of states is at about 0.4 filling of this first Moiré subband. And as I start to apply an electric field, this peak in the density of states moves towards half filling. And eventually, if I apply a sufficiently large field, it goes through half filling, and then it just keeps going on. So with this knowledge, if you now ask where in this phase space do you actually see insulating behavior, then the answer is we see insulating behavior when this peak in the density of states is close to half filling. So when the electric field is too small, it's on one side of half filling. When the electric field is too large, it's on the other side of half filling. And in both cases, this resistive peak goes away. And this resistive peak is only seen when the density of states has this peak that's close to half filling. And so this tells us then that this system is in a regime of moderate correlations. So it's not in the strongly correlated limit where band structure doesn't make a difference at all. And what helps it form this insulating state is the fact that the density of states is high, and that would naturally encourage the formation of a gap driven by correlations. And I should say this is a little bit of a diversion, but experimentally you can measure where this peak happens, because this peak corresponds to a sign change in the Hall effect, and you can measure where this sign change in the Hall effect happens and confirm that this theory is at least reasonably correct. We have good agreement there. And so this was the picture that we had in 2020 for why it is that you have insulating behavior in this set of compounds. And the picture is that you have moderate correlations in the system. And when you have a peak in the density of states that's at half filling, it encourages the formation of an insulating state. Okay, so after we got this result, one question that I had, was, so what? After all, we have lots of correlated materials, lots of them which are mod insulators, and the temperature scales, the energy scales are much more impressive than anything that I've shown you here. So, in many correlated materials, you can have insulating states that survive up to room temperature or even above room temperature. And all of these things exist in other materials. So you can ask what's special about these Moiré materials, or what could be interesting beyond just the fact that there are these insulating states present. And at least one thing that we know is that in most other materials families, one way of exploring a phase diagram, for example, if you want to explore a phase diagram as a function of doping and as a function of bandwidth, what you might very commonly do is to build a bunch of samples, each of which is sitting at a different point in this phase diagram, measure its properties, and then assemble the phase diagram by looking at the properties of all of these samples. And something that's special in these Moiré materials is that you can, within limits, explore this phase diagram simply by applying electrostatic gates. And so essentially within a single sample, you can explore this phase diagram without changing samples, without changing disorder. Now, I don't want to give you the impression that there is no disorder in this sample. There is tons of disorder. And in fact, this is sort of one of the least understood aspects of these materials, is how much disorder is actually there in the material. But at least for a given sample with a given disorder, I can tune through this phase diagram by using electrostatic gates. And again, if you think back to your good old correlated materials like cuprates or what have you, then often the most interesting phenomena happen not in the insulating phase, but what happens when you destabilize the insulating phase and you have some nearby metallic phase. And that's when correlations are still strong, but you still have metallic behavior, so you still have low energy degrees of freedom. And that's when many of the most interesting phenomena that we know in condensed matter appear. So this can be strange metal behavior or pseudo gap behavior or proposed spin liquid behavior. And so there's a natural question, well, can we see any signatures of any of these things in our Moiré materials? And I should point out that even in other correlated materials where the energy scales are much larger, it can be a delicate business to measure the properties of these phases. And so that's certainly the case here as well in these Moiré materials, is that they don't easily show up in many experiments. And so one needs to do quite a bit in order to establish the nature of these phases. Okay, so with that in mind, now what we can do in our system is we can tune through bandwidth and we can cause metal to insulator transitions, and we can tune doping and we can cause metal to insulator transitions. So let's cause those metal to insulator transitions and let's ask what happens to those metallic states when you're close to the insulator. And so this was what we set out to do. So here, for example, is that phase diagram here again as a function of electric field and as a function of density. And what we did is we went along a line. So here I go along two lines. One line is this vertical dash line, and the other one is this angled dash line. And at each point, what we do is we do a transport measurement. We measure what the resistance does as a function of temperature. And if the resistance starts to go up at low temperature, then we call that an insulating sample. And we can measure a gap from an Arrhenius fit to the resistance. And you plot that gap as you go at every point across this line in this direction and across this line in this direction. And if you do that, then we saw something quite interesting. You see that indeed there is a gap when the sample is insulating, but then when the sample becomes metallic, which happens here as a function of electric field, or here as a function of this diagonal line, it looks like that gap, at least within transport, goes continuously to zero and eventually vanishes. And so this gave us a hint that this transition between the insulator is here and the metal is out here, is a continuous transition, which is not, I would say, super common in other materials which show Mott insulating behavior. It's quite common that there would be coupling, for example, to the lattice degrees of freedom. So when you have a metal to insulator transition, you might also have a change of structure. And so very often these transitions would turn out to be first order, though not always. So here was an example where it seemed like, at least from measuring the gap, that this transition could be second order. And if this is second order, then if one is close to the metal to insulator transition, one expects strong quantum fluctuations at low temperature. And so we set out to see, can you see any signatures of these quantum fluctuations in transport properties? And so that's what I'm going to talk about next. So if this picture is to be believed, then there is this oval-shaped region where I have insulating behavior, and everywhere on the boundary of this oval-shaped region, I have a continuous metal to insulator transition. And so what I'm going to do is I'm going to take this particular cut, and for this particular cut, it's mostly the density that's varying. So I'm going to plot this as a function of this density, and I'm going to ask, what does the temperature dependence of transport look like? So here's what that looks like for that particular cut. So here is, I'm plotting this on the density axis. This is the resistance as a function of temperature here on the left. And on the right, I just take a derivative with respect to temperature and plot the same data on the left on the right-hand side. So first, if I look on the left-hand side, I see regions, this dark red here is insulating behavior. In order to define the metal to insulator transition more carefully, we look at the derivative, and where the derivative changes sign and goes through zero, that's where we define the metal to insulator transition. So you see that that's this dashed line. Everywhere in here, we define to be the insulator. Everywhere outside is a metal. And what we're interested in is asking, what does transport look like at the boundary between the insulator and the metal? And if you stare at this plot on the right, you will realize that close to this metal to insulator transition, the color here, the color is a measure of d rho dt, or the temperature derivative of resistivity. It's reasonably constant. And so if d rho dt is a constant, this tells you that rho is linearly proportional to temperature down here. And if you keep doping it further, I'll show you over a wider range, this T linear behavior of the resistance is lost, and eventually it becomes a T squared dependence of the resistance. And the same thing is also seen on the other side. So there's a metal insulator transition here as well. And here as well, you see the color is uniform, again telling you that you have T linear behavior. So again, this is a cut mostly along the density axis, along that axis. And so here are some curves showing you how the transition temperature decreases, goes to zero. And on this set of data, it's not super clear because all the dots have the same color. But let me skip and go to another set of data to make that point clearer. So this is mostly to show you that this transition goes down to zero temperature as I go to the metal to insulator transition. Okay, so now let me show you data over a much wider range of doping. So this is now, I'm sorry that the notation is now funky. So -1 stands for half filling, -2 stands for full filling of the first Moiré band. And then this is over a much wider range of temperature now going all the way up to 200 Kelvin. And I'm going to show you some cuts so you can see for yourself what the resistance looks like as a function of temperature. So let's start from all the way out here, which is very far from all of this correlation physics. So correlation physics is here. This is very far from that. So if I take a cut along this particular line and I look at resistance as a function of temperature, and I look at low temperature, then at low temperature, the resistance is fit well by a parabola. And if I go to some temperature, in this case, it's around 25 or 30 Kelvin, then it starts to deviate strongly from the parabolic form. And eventually at high temperature, the resistance just saturates and becomes a vegetable. All right, so now let me come closer to my insulator, correlated insulator. So at this particular point, once again, I see very nice quadratic behavior at low temperature. and deviation from quadratic behavior. Here, the quadratic behavior extends out to a higher temperature, about 70 Kelvin or so. So finally, if I really hit that metal to insulator transition, so this is where that metal to insulator transition is, and I measure resistance as a function of temperature, you can really see the linear slope. And since this original work, we've now looked down to about 200 millikelvin. That's the lowest temperature we've gone to, and we see linear behavior down to 200 millikelvin. Let me now keep going and let me go into the insulating phase. And if you do that, you'll see at low temperature, the insulating phase starts to kick in. So the resistance starts to rise at low temperature. But if I go just above where that insulating phase kicks in, I have a region of linear in T behavior. And then it again rolls off and becomes constant at high temperature. If I keep going to the other metal to insulator transition, once again, I see a nice region of linear in T behavior. In this case, extends out to about 25-30 Kelvin. And if I go even further into the metal that's at low density, I start to recover the T squared behavior at low temperature. Okay. So that's sort of the phenomenology of this. And I can put this all together in this plot. So this plot tells me where in this plot I have T linear behavior, where I have T squared behavior, and these gray regions are where I have insulating behavior. Right? And when I say T squared, I mean that the resistance can simply be written as A times T squared plus a constant. And when I say A times T, then it means that it can be written as A times T plus a constant. And in these regions up here, what this region means is that there's a transition from T squared behavior at low temperature to T linear behavior at high temperature. And if you stare at this, this looks very much like phase diagrams that are seen, for example, in heavy fermion materials, where you have quantum critical points. So there's a well-defined quantum critical point where T linear behavior is observed down to T equals 0 or down to the lowest temperature. And then this region of T linear behavior extends out from the quantum critical point in the shape of a fan, in the shape of a quantum critical fan. And when I go away from this quantum critical fan, I start to get T squared behavior, which is characteristic of a Fermi liquid. In our case, the difference is that I have two of these quantum critical points. I have one for electron doping, one for hole doping. And so you can see two separate quantum critical fans that merge together. The other difference is that here I have an insulating state instead of a metallic state on the other side of the quantum critical point. But otherwise, this looks remarkably like things that are seen in heavy fermions and other correlated materials. Now you can ask, are there any other signatures of quantum criticality in the transport? So one signature that's been investigated before in the context of heavy fermions is to look at the coefficients of the T squared behavior and the coefficient of the T linear behavior and see what they do in this phase diagram. And so we can do that as well. So wherever we see T squared behavior at low temperature, I can figure out what the prefactor is that goes before the T squared. So in this particular curve, for example, the prefactor in units of ohm per Kelvin squared is 0.68. And where I see T linear behavior, I can do the same thing. So for here, the resistance in units of ohms per Kelvin is 130 ohms per Kelvin. So if you plot out, and I guess this is shown for a somewhat dramatic effect, what the coefficients of the T squared and the T linear behavior do at different points in this plot. If I'm far away from this correlated insulating state, then that coefficient of T squared is basically very weakly dependent on the density. It's some number, it's 2 ohms per Kelvin squared. And as I approach the quantum critical point or proposed quantum critical point, you really see this thing explode and go up on this, in this case, by about 2 orders of magnitude. And again, this is something that has been seen before in heavy fermions. And the reason why we expect this to happen is that you're starting to hit the bottom of the band. And so the Fermi energy is basically going to 0. And that's what gives rise to this divergence in this coefficient of T squared. Similarly, when you approach the quantum critical point from the other side, also you see a divergence of this coefficient. In this case, it's not nearly as impressive. It's about a factor of 20, but still a pretty substantial increase in this coefficient. If you also ask what the coefficient of T linear behavior does, the coefficient of T linear behavior is maximized at the quantum critical point itself. And in the regions of T linear behavior that are away from the quantum critical point, so these are the regions of T linear behavior at moderate temperatures, that coefficient of T linear behavior is smaller than the coefficient of T linear behavior at the quantum critical point. And for what it's worth, if you take this number of 100 ohms per Kelvin and convert it to units of temperature, this turns out to be of order of what's called the Planckian scattering rate. Okay, so one other similarity between this system and other correlated materials can be seen in the magnetoresistance of these samples. So in a whole lot of correlated materials, it's seen that the magnetoresistance has some anomalous behavior as you approach a quantum critical point. So we can look for signs of this, and indeed we see signatures of this anomalous magnetoresistance in our sample as well. So shown here are a set of traces taken at different values of density approaching the quantum critical point along this particular line. And so here at minus 1.2, you're far from the quantum critical point, and at minus 1.02, you're very close to the quantum critical point. And what you see is that if I'm far from the quantum critical point, the magnetoresistance at low field is quite small, and perhaps not very obvious from this, but if you fit the magnetoresistance at low field, it looks like B squared, which is what one expects for a metal. On the other hand, as you approach this quantum critical point, you see that this magnetoresistance just explodes. And not only does it explode, it has a very pronounced bilinear character as you approach the quantum critical point. And you can make an ansatz for this, which was used successfully in the case of pnictides to explain this crossover from B squared behavior to bilinear behavior. And so in this, according to this ansatz, if beta goes to, if gamma becomes a very small number, then this becomes bilinear. If gamma is a large number, then this is B squared. And so you can indeed see this crossover happening from B squared to bilinear as you approach this quantum critical point. Okay. Now, everything that I told you so far was done as a function of density. You can do exactly the same experiment as a function of electric field. And indeed, you observe much of the same physics if you do this as a function of electric field. So these are curves done at half filling, exactly at the half filling point, but for different values of the electric field. And here as well, you can drive a metal to insulator transition. So up here is an insulator, down there is a metal. And if you look at the separation between the insulator and the metal, you'll see a region of linear behavior. I have to confess that when we took this data, we weren't looking for this. So we didn't take data with the best resolution. This is something that we ought to repeat. But within the errors of our measurement, it clearly is much more linear than T squared exactly at this quantum critical point. But if you dope it further into the metal, you can very nicely see a T squared start to reappear at low temperature. And so all of the stuff that I told you for the doping controlled metal to insulator transition is also true for the bandwidth controlled metal to insulator transition. And so the picture that emerges at the end of the day is that I have a region of insulating behavior, and this region of insulating behavior is bounded by a ring of quantum critical points. Now, I also want to remark, since there is a Van Hoff singularity in this system, one might ask how much of this is tied to where that Van Hoff singularity actually exists. So from Hall effect measurements, we can figure out where that Van Hoff singularity exists. And that Van Hoff singularity as a function of electric field runs away and eventually goes far away from the half filling point. But all of this physics that we see is really tied to the metal to insulator transition that happens close to half filling. It's not tied to the band hole singularity. Now, let me mention one more point, which is the following. It is just something interesting that we discovered. Whenever you have a metal, you can define a residual resistance. So normally what you would do is you would measure the properties of the metal to as low of a temperature as you can measure. And then if it's sufficiently low in temperature, you just extrapolate the curve down to 0 temperature, and that's your residual resistivity. Now, when you have an actual metallic state, we can do that and we can get an accurate value for the residual resistivity. However, when I have an insulator that appears at low temperature, you can still define a residual resistivity in the following sense. You go to temperatures that are above the metal to insulator transition, here temperature-driven metal to insulator transition, and you extrapolate this linear behavior down to 0 temperature, and you call that residual resistivity. And if you do that, so this residual resistivity as defined in this particular fashion doesn't know anything about the fact that there's an insulator at low temperature. So this is really a property of the high temperature phase extrapolated down to 0 temperature. If I plot out this residual resistivity in the phase diagram as a function of electric field and as a function of density, so that's a plot here of this residual resistance, and I compare it to where the insulating behavior is, you see basically a one-to-one correspondence. Right? So what does this say? What this says is that this linear in T resistance that appears above the metal insulator transition already knows about the fact that there's going to be an insulator at low temperature. So it's a predictor of the fact that there's going to be insulating behavior. And another way to say this is that we think that these are fluctuations of the same order parameter that determines the insulating state at low temperature. And I'll say just one last thing about this. If you look at this residual resistance, you'll notice that there's a fairly abrupt jump in this residual resistance as I go from the metallic phase to the insulating phase. So here, this is this jump in the residual resistance that you see as you go from the metal to the insulating phase. And I'll just say that this kind of jump has been predicted before in theories that predict spin liquid behavior on the insulating side of the metal to insulator transition. And this is perhaps some evidence that there's interesting fluctuations on the insulating side of the metal to insulator transition. But of course, it's certainly not sufficient to say that there's anything like a spin liquid there. One interesting question is how in these systems would one detect that there is actually a spin liquid there, because it's not a macroscopically large sample that one can do many of the measurements that one normally does. Okay, so let me just summarize this part of the talk. I've shown you that it looks like there's a ring of quantum critical points in this system. Some of the things that we need to do, we need to clearly identify what is the nature of this insulating phase and what's the nature of this metallic phase. And in this regard, magnetotransport actually shows you a lot of intriguing phenomena that we haven't fully digested. So I'm just showing you, for example, here, what the Hall effect does in the vicinity of this insulating phase. And it has some spectacular behavior as a function of density, which we are not quite sure what it means at this point, but it's something that we hope to unravel to understand better what these insulating and metallic phases actually are. Okay, so let me see how I'm doing on time. I'm at 3:47, which does not give me a whole lot of time. So maybe let me just spend a few minutes introducing you to this system, and I won't get into too much detail. And perhaps I'll bring up an important point, which is a point of disorder in these Moiré systems. So recently, this system of twisted trilayer graphene has gained a lot of interest. So twisted trilayer graphene, like twisted bilayer graphene, has been found to be superconducting by two groups, Philip Kim's group and Pablo's group. And twisted trilayer graphene is basically three sheets of graphene where the top and bottom layer, at least in the theorist's conception, are perfectly aligned with each other. And the middle layer is misaligned by some twist angle theta with respect to both of those layers. And let me skip over all of the details, but let me just make the point here, which I can actually make with this particular slide. In the theorist's ideal conception, this top layer and bottom layer are perfectly aligned with each other. But for anybody who makes a real sample, you know that this is impossible to achieve in practice. And so what's going to happen is that there's always going to be a small misalignment between these top layer and the bottom layer. And what this will do, if you think about it, is it will create two separate Moiré patterns, a Moiré pattern between the top layer and the middle layer, and a Moiré pattern between the middle layer and the bottom layer. And so in general, one expects two Moiré frequencies. And let me skip right over a whole bunch of stuff and just show you a cool picture for what happens in this situation. Let me jump all the way over to here. So what happens in this situation when I have, so this is now an STM experiment, is I have two of these Moiré patterns present at the same time. If you study the density of states in the system, you will find that this density of states looks like a granular superconductor. So let me jump right to the punchline of this. This is the density of states at the Fermi level where transport for this angle sees superconductivity. And you see that this object is basically looks like a bunch of grains that are not quite separated, but are connected to each other. So the point I want to make with this is just that disorder in these systems can be very interesting and very complicated. And it's one of the things that needs to be understood better. So with that, let me just conclude. Let me go up here and let me stop and take any questions that you might have. Thank you.
Thank you, Professor Pasupathy. The floor is open for questions. Okay, I think Professor Fisher, you had a question.
Oh, hey, Abhay, that's a lovely talk. So look, you know I'm not an expert at all on any of these twisted things. Can I just ask a practical question? Why did you say that samples below 4 degrees are less reliable? I've seen talks of people talking about magic angles and things which are less than that. I just wondered what makes that hard physically to do?
Yeah, so that's a good question, and the answer, at least I don't know precisely. Well, okay, so at least I know one aspect of this answer, which is think of how the Moiré basically breaks the band into subbands, right? The size of the gap for each subband is proportional to the superlattice potential that you impose on the system, right? That's the solid state physics. And what we know is that superlattice potential actually becomes quite strong when you go below about 4 degrees. And we've measured this experimentally from STM. And so what ends up happening is it's, on the one hand, it's kind of what you want. You want to reduce the bandwidth to nothing, right? But when you reduce your bandwidth to nothing, then a small amount of disorder completely kills you when it comes to transport, right? I think in optics, so there's beautiful work both from Feng Wang's group and Berkeley, as well as at Cornell. And in optics, you can get away with some amount of disorder. But as you know, in transport, you don't need a whole lot to really mess you up. And so in transport, we've had a kind of really bad time getting any metallic behavior in this at all. It's always insulating, right? And when you have always insulating behavior, then it's kind of, it's not a good place to start making statements about whether it's still linear or not.
I understand.
Yeah.
Okay, thanks, Abhay. Nice talk.
Thanks.
Okay, go ahead. You hear me?
Yes.
Can you go back all the way to the slide where you had resistivity, curl plot against electric field on one axis and filling on the other axis?
So this is the low temperature resistivity?
That's right. So there's also a reddish region at, away from half filling.
Here.
What that is.
Are you referring to this region where the mouse is right now?
Yes.
Yeah, so this region, so the reason why we don't have any data here is that our contacts go bad. And so you can see, I hope you can see all the way along. So, okay, so this curve is generated actually by sweeping the two gate voltages, and then you convert that to density and displacement field using geometry. And I hope you can see that there's this line is a line of constant gate voltage actually. And as you go from here to here, the contacts turn on. And so the reason we believe that we see this, and we don't see this in all of the samples, for this particular sample, we see this region where the resistance is high, but we don't think this is really insulating behavior related to this insulating state. It's just the contact turning on. That's really one of the bottlenecks in this, is getting good contacts.
Right. I have another question actually. So in your metallic states, does the resistivity always seem to saturate at something of order, whatever it was, 5-10 kilo? Does it ever,
Yeah.
feel bad?
Yeah, so that's something that we don't really understand. So we see in all the curves that the resistance kind of saturates at this 5 kilo ohm, 6 kilo ohm. It's not a universal number. You can see that it varies as you go across the phase diagram, but it's on the order of 5 to 6 kilo ohms, which is it's not a large number, right? It's not many times E squared over H. But it does saturate. So yeah, and it's kind of interesting because, okay, so if I go back to the band structure, so if I look at this, you'll see that this first band is not actually completely isolated from the second band. There's a little bit of overlap. And so in graphene, for example, it's been postulated that when you have a real gap between the first band and the second band, then of course, when you excite across that gap, then you start to short the transport. You can have saturation. We don't think that's a reasonable explanation for having saturation in this case. But why it saturates, I don't really know.
Any other questions? Yeah, go ahead.
So I have a question. You mentioned in your talk that the gap at full filling is much smaller than half filling, and I was just curious to hear your current kind of understanding of why that is and how generic it is, what it depends on, whether it's material dependent or twist angle dependent, or is there a simple physical picture?
Yeah, so I think it's related to the same physics. So in reality, there's no real gap because the second band basically starts to get filled right around where the first band finishes. And so that's the reason why there's no real gap. There's another channel for transport. And again, as you start to lower the density, lower the twist angle, then this Moiré potential starts to become larger, and then you do start to get gaps at half filling. But that's also the region where our overall transport starts to go bad. Does that make sense?
Yeah, so the prediction is basically if you're at a low enough twist angle, you should see a real gap in the spectrum, but it's difficult.
Yes, so we can see from STM that that's true, but not from transport, unfortunately.
I see. And maybe one other follow-up. Have you, these are dual gated devices. Have you looked at thermodynamics signatures of compressibility? Transport can be a little fraught given the disorder that you showed in the trilayer portion.
Yeah, so we have some capacitance measurements. And I think the only thing that's different in the capacitance measurements from the transport measurements is we see in some samples signatures of insulating behavior at fractional fillings, like it's been seen by the Berkeley and Cornell folks in other systems. But otherwise, in this range of angles, the capacitance signatures of everything are very consistent with what we see from transport.
Okay, thanks.
Sure.
Any last minute questions? Yeah, go ahead.
So you mentioned STM experiments on these systems. Do you know quantitatively that this twist angle disorder is better or worse in these systems?
So when you are at these angles, like 4 or 5 degrees, twist angle disorder is not terrible. So you can get sort of half micron or 1 micron regions, which have pretty uniform twist angle. For something like twisted bilayer graphene, we have never seen a 1 micron region uniform, free of twist angle disorder. It's a mystery to me how the thing works at all. But in these things, when you're at 4 or 5 degrees, it doesn't feel too bad. The one thing that's different about the TMDs, I don't have a slide, I'm sorry about this, is TMDs have point disorder. So you have point defects in TMDs, which you don't have, or almost nothing in graphene. And what point defects will do is they will basically shift the band edge locally. And that can be a very serious thing. So if you have a slightly bad sample, which has more point defects, then if you go from site to site on the Moiré unit cell, the potential energy of each site can be off by more than the bandwidth of the Moiré pattern. And so this happens, for example, in MOS2. So we tried hard to make samples out of MOS2 because there were predictions that it would realize a Kagome lattice, blah, 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 but never worked because the point disorder was just so bad that it was garbage.
Okay. I think I have just one quick last question. In the last slide, we showed some amazing STM data on twisted trilayer graphene. So I think related to the topic of disorder in these systems, is it that the encapsulation of HBN and how that is aligned with the graphene, is that also something that perhaps could lead to another Moiré, and is that something that matters, or is it just a lower priority?
Yeah, absolutely. It could matter. So, so what happens is when you have 2 Moirés that are sort of close to each other, then instead of the system forming 2 separate Moirés with very close wavelengths, what happens is you form a region of commensurate stacking, and then you have a discommensuration, a soliton. And that's what happens in twisted trilayer graphene. We've seen something like this in magic angle bilayer on boron nitride, although it's not really in the soliton regime yet. But yes, absolutely, that does have a pretty significant impact. And interestingly enough, the biggest impact is actually, if you look at this closely, you'll see that this particular unit cell has a much shorter lattice constant than all of the other unit cells. And so this unit cell, if I measure the twist angle of this unit cell, sorry, I'm going through this, the twist angle of this unit cell is much larger than the twist angle of the other unit cells. And so this creates this network of twist angles, which is very interesting phenomenon. And I expect something like this also to happen in magic angle bilayer on boron nitride, although we haven't measured that carefully enough.
Excellent. Thank you. Thank you once again for the excellent talk, and thank you everyone for attending.
Thank you. Bye.